we're asked to calculate the concentration of a solution. Let's first identify what type of solution it is so that we can determine the calculations we need to do. We see we have a pretty high concentration of ammonia. Ammonia is a weak base. And we have a pretty high concentration of ammonium chloride. Ammonium chloride is going to dissociate into solution and give us ammonium ion. So we have a weak base and its conjugate acid. They're present in high and sort of equal concentrations. We have a buffer. Now we're also told that this is a buffer, but we're not always going to have that luxury. So we want to practice recognizing what type of solution we have in the beaker. It is a buffer. It's Henderson-Hasselbalch equation to determine the pH, but we only know the initial concentrations, the concentrations that exist prior to adding a relatively hefty amount of a strong acid to 1 liter of the buffer. So we're going to solve this in the same way. We'll calculate our initial moles of our weak base and our conjugate acid, determine our new concentrations after the buffer has absorbed this amount of our acid, and then we can calculate our final pH using the Henderson-Hasselbalch. So we've calculated our initial moles of our weak base and its conjugate acid. We're adding a strong acid to the buffer. The strong acid will react with the base part of the buffer. All right, so we've predicted our products. We have a strong acid reacting with a base, and we're going to produce its conjugate acid. So the water loses an H+, the ammonia gains an H+. Here are our products, ammonium ion and water. Again, we're going to use a BCA table to help with our bookkeeping. We've added a lot of acid. We've added 1.5 moles of H3O+. And initially, we have 3 moles of ammonia, and we have 2 moles of the ammonium ion. This is before a reaction of the buffer with the added acid. When the added acid reacts with the buffer, we're going to lose all of our added acid. We're going to lose that much of our base, and we're going to gain that amount of our conjugate acid. So that after the reaction is complete, we no longer have any of the strong acid. We've lost a good portion of our base, and we've gained some of our ammonium ion. So now we can apply the Henderson-Hasselbalch equation to determine the pH. I realize that there's an alternative version of the Henderson-Hasselbalch involving POH, but I end up getting confused when I try and use it, so I don't. So what we find when we are looking for a value of pKa is that we don't have listed in our textbook anyplace the pKa of ammonium chloride. Instead, what we have is the Kb of our base. So we're going to have to convert our Kb to Ka in order to use the Henderson-Hasselbalch equation. So we can convert to Ka in this usual fashion. Alternatively, if we wanted to, we could have calculated the pKb and subtracted it from 14 to get our pKa. Either way would result in the same answer. So we can sub in our values. And again, we can substitute in our moles of base and acid because we recognize that they're both in the same solution. So our moles of base is 1.5, our moles of acid, 3.5. So our pH becomes 8.887 or 8.8. 8.89. If we were to calculate the initial pH according to Henderson-Hasselbalch, it would be 8.41. So we're going up less than half a pH unit when we've dumped in a ton of strong acid.